So we've built a virtual simulator which predicts the number of people getting affected by a particular virus or pathogen. So let me give you a tour through what we've built. So the name of our application is EpiControl AI. So Epi is basically epidemiology. So we've calculated gamma and beta on the basis of epidemiology using the mathematical equations. So we have a population box which we can set from 0 to 10,000 people. Initially affected people by that pathogen were 10. Initially exposed people means the people who are infected by that pathogen, but they cannot transfer their disease to another susceptible people were 20. The transmission rate is the number of susceptible people getting infected by a disease. The recovery rate is the number of infected people getting recovered from a disease. Then you can set the simulation timeline for how many days do you want to simulate. And we can select a simulation strategy as well. So here we select no intervention. We run the simulation. When we run the simulation, we observe a graph. In the graph, we can see the infected people on day 70 or 2000, approximately 2000. The exposed graph as well as the received, susceptible, and infected. When move downwards, so this is a map of India which indicates that the number of infected people in Delhi were 347. In Lucknow were 86. The red light area highlights that there were more infection caused in these areas than the others. So if we change the strategy, for example, we implement partial lock and run the simulation. So we can see that the recovery rate has drastically increased because of lockdown. And we can implement other strategies as well. If we implement a full lockdown strategy and run the simulation, then we observe that all come on a single line because there is no human contact at all. Similarly, when we run a vaccine campaign and simulate the model, we observe that the recovery rate is drastically increased due to vaccination drives. So we can observe that the number of cities are listed here and the number of people infected are as well listed. So this graph is according to the map displayed. Similarly, these alpha and beta values are in universal values which can be selected for a particular disease. So, for example, for smallpox, our beta value is 0.2 and our gamma value is 0.1. And when we run the simulation, we can observe the graph. So basically, our model is multi-use case. So it's just not for a particular disease, but it's for all the diseases that can be caused to humans. That
Stop. And you might ask this question that did we use any data set to train this model? So no, because RL model does not require any data set to be trained because it is a self-learning model. What we actually did is we created a virtual lab, and in that the model learns by itself, just like we just in the manner we teach a pet how to do a handshake by by rewarding the pet treats, that is treats and penalty. This is a virtual lab for disease spread simulation. And the USP, our main USP is the map wise uh, uh, segregation of infected people, uh, of number of infections region wise, such as in Jaipur we have uh, Lucknow, we have Ahmedabad we have infected for 24 people, and in Mumbai we have 49 people infected. It will tell on which day the mutation event might occur. So, how did we tackle this problem? On this selected virtual population, for example, here it is 10,000. On this population, what we are considering that the majority of people, like 80%, if 80% people are getting infected, then the virus will mutate. This is a parameter that we are considering to solve this to solve this problem, which was expected in the problem statement. Thank you. Thank you.